In section 2.7, we're going to be talking about graphing techniques. This is a really important lesson. We've talked about factoring being the most important lesson in math, or the most important topic in math, and how to graph is the second most important topic. We'll be talking about this especially when we get to trigonometry. So let's learn it right the first time. Parent graph was the last lesson. What a parent graph was, it's just the original graph. So remember we talked about if you have y is equal to x squared, that looks like a parabola. If y is equal to the square root of x, it's like a hook. Y equals the absolute value of x is a v. Y equals the cubed, x cubed is kind of like an indecisive parabola. And then y is equal to the cubed root of x looks something like this. Those are, in general, the shapes that we're going to be transforming or just moving around. So let's get to this. I mentioned the word transform. What a transformation is it's a change in a graph. Now you could change a graph a few different ways. One thing you could do is you could translate a graph. And when we're translating a graph, we are adding or subtracting. And translation just moves the graph left, down, up, or right. Of course, if you want to move it on a diagonal, you can move it right and then you can move it up, or combination. The second thing is a reflection. You could reflect a graph. This happens when you multiply by a negative. And we could reflect over the x-axis, and we could reflect over the y-axis. In general, when we're reflecting over the x-axis, it's negative on the outside. And when it's a reflection over the y-axis, it's negative on the inside. Let me just show you quickly what this looks like. If we had a parabola 2 units to the right, and we were going to reflect it over the x-axis, it would look like this. Just imagine like folding it over. If we were going to reflect it over the y-axis, just imagine kind of flipping it over. So folding and flipping, I use those words interchangeably. But imagine that axis is the axis that you're folding it over, right? Okay, so let's talk about the third type of transformation. The third type of transformation is called a dilation. And we get a dilation anytime you multiply by a number other than 1. When we have a dilation, we could either have a stretch or shrink. Now we could stretch over the x-axis in the x-axis direction or over the y-axis. We could shrink also over the x-axis or the y-axis. When I say shrink, imagine you're bringing the graph closer to the midsection from either direction. When I say stretch, imagine you are bringing the graph away from the midsection. So if we had the graph y is equal to x squared, generally looks like this. Let me show you what a stretch and a shrink would look like over each axis. Now the x-axis goes this way, right? And if we take our graph and we move it away, a stretch, over the x-axis, it's going to look like that. It's going to be wider. If we're going to stretch it over the y-axis, imagine just kind of grabbing the top and bottom of the graph and pulling away. The graph's going to look narrower. A shrink over the x-axis, imagine compressing the graph. It's going to look narrow. And a shrink over the y-axis, imagine holding the graph on top and bottom and bringing your hands closer together. So in general, what I want you to notice here is that a stretch over the x-axis looks similar to a shrink over the y-axis. I'll write wider here in a second. So they're like opposites. All right, and I want you to notice also that a stretch in the y-axis, which makes it narrower, is similar to a shrink in the x-axis. So now let's talk about what actually causes these to happen. So in general, when we have a function, we could use absolute value just as our basic function. We could put numbers in 4 different places. We could put a number here, 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 and here. All 4 of those numbers do different things. Whenever you see adding or subtracting, that's a translation. So we'll start with C first. If you're adding on the inside, if you see plus C, you're going to the left. If you see minus C, you're going to the right, that number of units. With D, that causes the graph to go up and down. If D is positive, you go up, negative, it goes down. If we're going to use more general notation, if D is greater than 0, the graph translates up. If D is less than 0, the graph translates down. If C is positive, we go left, and if C is negative, we go right. Now the A and the B can get a little bit tricky. So let's start with the A. Just separate it here. If A is positive, the graph opens up. Okay. If A is negative, the graph reflects over the x-axis and it opens down. That takes care of our reflection. Now, if you ignore whether it's positive or negative, so let's put absolute value there. If the absolute value of A is greater than 0, that's called a vertical stretch. So you look at our table above, but a vertical stretch is going to make the graph narrow. All right, so that's, when we're talking about y-axis, that's vertical. We're talking about x-axis, that's horizontal. So it's going to be a vertical stretch, and the graph is going, and I'm sorry, I meant when it's greater than 1. It's a vertical stretch, and the graph gets narrow. If the graph is less than 1, meaning like a fraction, like 1/3 or 1/2, this is going to be a vertical shrink, and the graph gets wide. Now let's move on to B. B is a little tricky. First thing we have to do with B is we have to factor it out if not 1. And we'll see examples like that in a minute. If B is negative, what that does is that reflects over the y-axis. And we talked about a reflection. If you ignore the sign of B, if B is greater than 1, that's called a horizontal shrink, which also makes the graph narrow. So you can see that these have similar effects, even though one's vertical, one's horizontal. And if the absolute value of B is less than 1, that's a horizontal stretch, which makes the graph wider. So now let's take a look at what some actual graphs look like. What if I asked you to graph, let's say y is equal to x squared plus 1. Now in my class, it doesn't have to be exact. Let's just generally give it a sketch of what it looks like. Well, x squared is this kind of shape, right? If you have plus 1 on the outside of the function, meaning like x squared is the function, so the plus 1 is on the outside, that would be d. D is what I consider the outside, and plus c is what I consider the inside. So with absolute value, if it's inside the absolute value, it goes left and right. If it's outside, it goes up and down. So this is plus 1 on the outside of the function. So this is going to move the graph up 1. That's what it would look like. What if we had a graph like y is equal to x minus 3 cubed? Well, cubic graph looks like this. And you can see the minus 3 is on the inside. So if it's on the inside and it's minus, we're going to the right. 3 units. 1, 2, 3. And you could see, I mean, this isn't hard. It's, like rules you have to remember, but really that's all math is. If you can remember the rules, you'll get it right. What if you had a combination? So if you had y is equal to the square root of x plus 2 minus 1. Well, square root's our function. Square root looks like a hook. The plus 2 moves the graph left 2. Minus 1 moves our graph down 1. So it's going to look like this. Left 2, down 1. Like this. Left 2, down 1 would look like that. That's all there is really to it. Take a look maybe at some reflections or some dilations. What if we had y is equal to negative 2x squared? We're multiplying by negative 2, so that could be a reflection and a dilation. X squared looks like this in general. The negative is going to reflect over the x-axis. So the negative does one thing, and the 2 is bigger than 1. So look at our notes. If the outside number is bigger than 1, the graph's going to get narrow. So maybe a better graph would be like this. Now, if we wanted to get it precise, we could plot points. So if you plug in 0 for this, you know that y is 0. If you plug in 1, y would be negative 2, right? And negative 1, negative 2. So, I mean, you could make it precise or exact if you want, but that's not necessary for me. You could see my guesstimation is about what it actually is. And let's maybe do one more graph. Let's say y is equal to the absolute value of negative 2x plus 4. Now, one thing I noted in the notes is that if there's a number in front of x, we have to factor it out. So you might look at this graph and be like, well, it goes to the left 4. You said if you have plus 4 on the inside, it goes left. But before I said that, we have to factor out negative 2. So we get y is equal to the absolute value of negative 2 times x minus 2. We're dividing both of these terms by negative 2. So instead of going left 4, it actually goes to the right 2. So here's our absolute value graph. It's going to the right 2. Now, this negative caused it to reflect. So you don't have to worry about that on the inside. We're not going to reflect it again. Technically, the graph went left, and then it reflected over. It's a little tricky on the inside. Bottom line is, if you factor it out, just go by what it is over here. It's automatically reflected. But then the 2 on the inside, if that number is bigger than 1, the graph's going to get narrow. It's just like if the outside is bigger than 1. although this is technically a horizontal shrink, the graph's still getting narrower. So I'm just going to draw the graph maybe a little narrower. And if we wanted to make it a little bit more precise, what we could do is we could get maybe the y-intercept. The y-intercept, we would put 0 in for x, and we'd get y is equal to the absolute value of 4. So the y-intercept would be 4. So well, that's what the graph would look like, and that's good enough for me. What I wanted to do to finish up today is talk about symmetry. Now, what you need to know for this class, there's all different types of symmetry. What you need to know for this class is what's called an even function and what's called an odd function. Now, when we talk about an even function, it's symmetric over the y-axis. So think about any kind of graph that the y-axis cuts in half. You know, like absolute value, and maybe x squared. And an odd graph is a reflection over the origin. And this is a little bit trickier to see. But when we talk about reflecting over the origin, let me show you. This is the graph y equals x to the third. If you take this point right here and you reflect it over the origin, so take it and just head to the origin, keep going, it'll actually be the same point as right there. And that happens with any point along this graph. If you just retrace it over the origin, you'll get the same thing. So the tricky part is, how do you know if something's even or odd? And it's actually pretty easy to figure out. We talked about function notation, f of x. So if the original function is f of x, a function is even if you plug in the opposite of x and you get the same exact function back. So let me show you what I mean here. Just move this guy down a little bit. So watch, ready? So these, instead of calling them y, we'll call them f of x. Okay, so what's f of negative x? Well, what's negative x squared? Well, it's x squared, right? So you see how f of negative x is the same exact thing as f of x? That's why it's called even. It works the same with absolute value. That's why it's called an even function. A function is odd if you plug in the opposite of x and you actually get the opposite of f of x. And sometimes it might require factoring, but it's not hard math, so watch. If we plug in f of negative x, what's negative x times negative x times negative x? It's negative x to the third. And if you notice, that's exactly the opposite of f of x, right? So that's what it means for a function to be odd. Let me give you a few examples and we'll figure out what their symmetries are. So let's determine whether the following are even, odd, or neither. And generally, we always have a question like this on the exam and the final exam, so it's important that you know what you're doing here. So let's take a look at a first example. Say f of x is equal to x squared plus 4. Well, if it's even, what that means is if we plug in the opposite of x, we'll get f of x, the same exact thing. If it's odd, if we plug in f of negative x, we'll get the opposite of f of x. And if it's neither, we'll just not get either of those. So let's see what happens. Let's put in f of negative x, and we get negative x squared plus 4, which is x squared plus 4. Well, that's the same exact thing, right? So this would be an example of an even function. We put in the opposite of x, and we got the same exact thing. We only have to do it once. If we got like negative x squared plus 4, then it would be odd, but that's not what we got. What about a problem like this? Let's say x is equal to, let's do this. Let's say f of x is equal to x to the third minus 1. Well, let's figure out what f of negative x is. F of negative x is negative x to the third minus 1. Okay, so that's negative x to the third minus 1. Well, it's not the same thing, so it's not even. If it was even, it'd be x to the third minus 1. If it was odd, we would get the opposite of x to the third minus 1, or negative x to the third plus 1. So it's not odd. So if it's not even and it's not odd, we would say that this is an example of a neither. It doesn't have any kind of, it's not even or odd. And we'll do one more. What if we said f of x was equal to x to the fifth minus x to the third plus x, something like that. Now if the graph was even, we would expect to get the same thing if we plugged in the opposite of x. If the graph is odd, we would expect to get the opposite of x to the fifth minus x to the third plus x, or negative x to the fifth plus x to the third minus x. So let's see what happens. If we put in negative x, we get negative x to the fifth minus negative x to the third plus negative x, which is negative x to the fifth minus negative x to the third minus x, or negative x to the fifth plus x to the third minus x. We could take out a negative from this, and we could see that it's exactly the opposite of what we started with. That's why this would be an example of an odd function.